But I will introduce Professor Dr. Noura She's assistant professor at Durham University in Great Britain, and also she's the head of artificial intelligence and machine learning at Evergreen Life. Her interest is natural language processing, optimization, and other complex machine learning problems. Yeah, and it's not the first time that Professor Moubayed is at NGSchool. She also attended NGSchool several years ago before the COVID, and we had a really nice panel discussion, ethics in machine learning, and there's a video of this. You can check on Facebook, but now you can see. You can learn from Professor Moubayed in person.
Thank you. Yeah, so this school is one of my favorites, to be honest. And whenever I get invited to come here and see everybody and give a talk, I get super excited about it. And I can't say no. It's just a pleasure to be among you all. So today I introduce you to natural language processing. In 1 hour and a half, it's very difficult to put like maybe 20 hours worth of lecturing, but I'll do my best. Feel free to interrupt me anytime and have any discussion. Most of your questions I'll probably answer. I have no clue, but we can work things out together. Yeah, so to start with, what is language? Language is human beings, right? This is our reflection of what we have in our heads. How many times you had a conversation with your friend or your mom or your sibling, like people are very close to you, and you end up saying, "Oh, you misunderstood me. I didn't say that. Don't put words in my mouth." Think such phrases. I'm sure at least you've done it a couple of times in every week, maybe, right? Why do we do that? Maybe because we're very bad in generating word embeddings for our thoughts. Not very bad, but not very accurate. That's why we need to correct people's understanding. So intentions, most of the time, don't 100% reflect intentions, perception and intention. And machine learning or natural language processing comes into building embeddings of our words that vaguely represent our ideas and thoughts. Okay? Just show you that the process starts from here, and sometimes we'll ask, is this really like when we annotate a data set, for example, about toxicity or sentiment even, and ask people, is that positive or negative? This is perception. It's never really accurate because the only person who can answer this is the person who wrote that statement, right? Because they know their own intentions the best. So just to show you that we start from a very inaccurate place. And we try to build some models to make some understanding of perception mostly. So language is complicated because we're complicated and cultures are different. And what people understand from statements like students who can serve grandparents. For someone who's just learning English, they will think that in this country people eat their grandparents and that's totally legal. Right? But like for someone who came across the statement and would understand maybe it's a grandparents and they're cooking a meal for their grandparents. Right? So, but syntax-wise, like serving and cooking, I don't know, like an apple today or something. Pretty much very similar syntax. And another example, samples say cops kill man with knife. So do they stab the man with a knife to death, or the man was with a knife and therefore they killed him? Also, it's not clear, right? You can't really 100% say it is this or that, except if you read the context and know that police were less likely to stab people in the street, hopefully. Also, call me a cab, and okay, you're a cab. So like, call me Noura. What's the difference between call me a cab and call me Noura? Context, right? And cultural context as well, because maybe in different cultures you don't use the same phrases, you use different phrases, but has the same level of ambiguity. Yeah, so to start with, it is pretty much vague and ambiguous, and then language is also evolving. So maybe someone reading the Bible will hardly understand anything, except if they studied some linguistic stuff around it, and then reading Shakespeare, they will also struggle. And then maybe someone my age reading this kind of abbreviation will pretty much struggle and start Googling stuff. But this is language. Language is evolving every day. And probably today we have new terminology that we haven't heard of yet. So that's the thing. As humans, we struggle in coping with how the language evolves and how fast it does that. But we want somehow to build models that can cope. He's better in coping than us, maybe not better in understanding, but better in coping with the evolvement of the language. So I usually cover this part and ask my students to guess. And they reach the I don't know, and then they stop. they start being on their phones trying to do the rest. That's so cool because they're like early 20s, and if they don't know, I feel fine about myself, less sorry. Also, language models are everywhere. You might think, maybe this is like a cutting-edge technology, therefore I'll worry about it in 10 years' time when it comes to things I use on a daily basis. Well, maybe you already know that you're all using language models on a daily basis. And even if you are the person who is like, I'm not doing any social media, I have 0 social media apps on my phone or laptop or blah, blah, blah. But you're still texting, that's a language model behind it. You use Word or PowerPoint, I'm using PowerPoint, there is some language models behind it when I type things. So yes, they are everywhere. And most of the platforms is like career-oriented, like LinkedIn or social media like Twitter and Facebook and so on. They heavily use language models in many tasks, like for example, suggesting jobs for you, or suggesting your profile to some recruiters on LinkedIn, or filtering toxic language on Twitter, right? And they don't succeed most of the time, but they do use. Also, Google Translate is the most popular translation app out there. So it is everywhere. So the main task is like we as humans embedding our thoughts in words, and now the machines will have to embed these words in numeric format, right? Because machines will not understand our human language and words. So this is the main task for language models, right? And full stop. Move the words, the chaotic words and thoughts, as in words, into some format of numbers so we can train some models on that. So to start from like a very early stage, early stage in the literature, the first step, we had a lot of text, and the first step was normalizing that text. Normalization means maybe you have an uppercase and lowercase, and how can you make them all in the same format? So usually you would go to lowercase, but not necessary. You might choose to do the other way around, which is fine. When you normalize, you already corrupted a lot of text, because, for example, US will become us, right? So there is, in every step, pre-processing step, you are corrupting the text to some extent. Then tokenization. Tokenization is splitting then your sentences and phrases, paragraphs into separate words. You'd usually use punctuation or space, like white spaces, to separate the words and do the tokenization. And then you remove stop words. Usually, you don't have to if you don't want to. and stop words are these useless words. You might disagree, but that's how you perceive them useless, therefore you remove them. And maybe words like is, or maybe they're useless, maybe they're not. You might argue that they're not. This is arguable issue, right? But when you remove stop words, you remove a lot of repetition of words in a document, because big part of every document and every sentence we write will have the as, blah, 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 he, she, and they're mostly considered stop words. Some people argue that negation is also stop words, like not. But then when you remove not, you kind of corrupting the context and the meaning even more. So you need to be careful. There are pre-made stop word lists out there to use or get some insights from, but most of people would take one stop word list and adjust it the way they want, depending on your application. And then you have like stemming and lemmatization, and stemming, and both of them would just return to the root of the word. Stemming is much easier because it's rule-based. So for example, walk and walked, you just remove the ed at the end of the sentence. Mostly done with regular expressions, like remove ing, ed, and so on. But to find out the lemma of the word, you need a dictionary. So you would move from something like R and S to B, and this is not rule-based. You definitely need a dictionary. That's why it's more expensive to compute or to find. So this is the olden days, okay? But this still works, and in many applications when you have small data set, you still prefer to do this kind of stuff. So now we have tokenized words in some format, most of the time not even readable after stemming and lemming. But then what do we do to move to numbers? There's many ways to move from words to numbers. There's the binary embedding, and the binary embedding is just to have all the list of words you have in your corpus or whatever pool of documents you have, and you represent it in a binary code, like 1 if it exists in any capacity, and 0 if this word does not appear. Right? So you have a very long vector, and each value would represent a specific word in a dictionary, and 1 it's there, 0 it's not. But then you feel like, well, this is really bad, because what if the word appears like 10 times more, and this is the word I'm really keen to read documents about. So I'd like to read the documents that it appears in most than the one that maybe appears in just once, just to run those documents. And then you do the row count, you just count how many. And then it becomes like an integer embedding for your dictionary vector, where you have the counter instead of the binary values. And then you would criticize that and say, okay, this is a row count, but what if the document is too big? And maybe it has like hundreds of thousands of words and it appears 10 times, but maybe another document with 20 words and also maybe it appears 2 times. Maybe I'm more interested in the small document because it says more proportionally than the one that's massive and it appears more in it. So that's when you calculate the frequency and you use the row count and divide by the size of your document. How many terms there is in your document, how many separate tokens there are in your document. Right, and then you get like comprehensive measure of the value of this word in that specific document. And you use the log to dampen the impact of what if it appeared all the time. And maybe when it appeared like 100 million times, it's the same as it appears 10,000 times when you reach that stage with a big number. It's a good idea to use the log. It's 1 plus because you could get a log of 0, right? But we also want to criticize. I like moving slides with criticism because it's like that's how science gets developed. And also, this is not very accurate because, okay, it shows me that this word appears more in that document, okay? And this is more important document therefore to me, and then I have like, this is the return document. But what if it is a stop word that I decided not to remove and it appears in all documents? Maybe I don't care about it anymore, right? Because it appears in all documents and it doesn't distinguish documents from each other. That's when inverse document frequency comes into the equation. And you simply take the term frequency, as you saw in the previous slides, and multiply it by the inverse document frequency. Inverse document frequency takes into account that rare words are more important than common words. So common words that appear in all documents should have less importance than the rare words. And they just divide the number of documents you have in your entire corpus divided by the number of documents that this specific term you care about appear in them. Okay? You calculate the log of that and you multiply this value with your term frequency. And here you factor in how common or rare the word in a corpus or set of documents, and also the frequency of the word in a specific document. So, good stuff about those. This does work, by the way. And if you have like a small data set and you're in a hurry and you want some good results, but not mind-blowing, use that and it will give you a really satisfactory result. Okay, so good result. It's a very good baseline to start with. It's white box, pretty much explainable based on counting, nothing fancy. But it has some bad problems. For example, sparsity, because every document will be represented by the entire vocabulary, right? The entire vocabulary. And you might end up with tens of thousands of different tokens, and therefore that's the size of your vocabulary. Each document will be presented in that, but not mostly. Most of the vocabulary will not appear in a single document, right? So you'll have a lot of zeros, and that's sparsity. You don't like sparsity much, and you don't like to have such massive vectors to deal with at once. And also the pre-processing steps we talked about, it does corrupt the meaning and the context of the sentences. And most of the time, it makes them not human readable anymore, right? Like before you saw last university term to universe or inverse, or it just corrupts the meaning at some point. So there are disadvantages, but for many applications, it's still fine to use. So we're going to move to neural learning, slightly more advanced domain, and that's how can we get rid of the very long vectors and the very sparse vectors and move to something shorter and more dense. So it's easier to deal with from a machine learning perspective. So neural embeddings offer that, dense vectors. But then you say like, okay, every model, because that's a neural model, right? Every model needs a task to solve in a way. So we can do some training for the hyperparameters we have or weights. So what is the task? And in text, it's very easy to find a freebie task, which is predicting words that exist in your text already. You don't have to hire people to sit and annotate your task, your data to come up with a new task to train your model. You actually just look at the text and start predicting maybe next word, maybe missing word, depends on how you like to formulate that. But it's a free task, and we call it a toy task sometimes. There's many ways to train those. The most common way is the continuous back and forth and escape routes with negative sampling. And I'm gonna explain briefly the two concepts next. One important factor is the sliding window. because if you want to predict the next word, for example, the sliding window will define your context. It's like a context window. You don't want to predict 10,000 words after a specific word, or if you take 10,000 words before a specific word to predict that. Maybe it's just too big, and most of it is already out of context. And so the window will decide where to look. So, one of the basic figures for that is how do you represent your input? It's maybe, so for skipgram and continuous backward is opposite of each other in concept, but same, very similar predict words. Skipgram, you would start from a word that you're interested in, and you try to predict the context around it within a specific window. Let's say your window size is 4, and you have that specific word in this window, then you will have 3 context words. From this word, you want to predict the 3 context words. So input is your target word, output is your context words. Continuous back and forth is exactly the opposite, where you start from the context words and you want to predict a single target word. So skipgram is more expensive because you do more, you don't just target a specific word, you target multiple words, and if your window is big, that will become difficult to train sometimes. But again, you can represent with one hot encoding, for example, the input just to point at this word, this is the word of interest to me, and then you split out probabilities. The highest probability would be the winning word, or the highest word, depends on the window size you have. Training is repetitive in iterations until your model converges or it reaches satisfactory performance. But remember, we spoke about we have words, machines don't understand them, and we want to generate some kind of numbers. We didn't do that, right, so far, because we're doing some predictions. So the idea is just to take your hidden layer. You've done some deep learning, or you're going to do it. You've done it, or you're going to do some deep learning. So I'm not going to worry too much about the deep neural network mechanism. I'm going to learn about this, I'm sure, or you've already learned yesterday. But you will have some layers, and you take the middle layer and you say, this is my embedding. That's it. And you are free to decide the size of your embedding vector. So here it's 300, and this is for word to vec, the most common embedding vector size. But you can say, well, 300 is too much, my corpus is small, I don't care about that. 300 representation, I'm actually fine with 50. You can retrain and decide that your middle layer is of size 50. And then you get a vector representation of 50 values. Okay? So you train this, you use the middle vector to represent your word. You represent your target word. Okay? Yeah? Will that work in reality? Because this seems very arbitrary to me, at least. Right? You just have some neural network, a toy task, throw the data at it. Okay, and where's the numbers? Let's take the middle layer. Kind of. Right? Very arbitrary because this word seemed to work quite well. So if you visualize this middle layer in your model with heat maps, for example, because that's easy to visualize and comprehend, you'll find there is a lot of similarity between the embeddings of woman and girl, boy and man, and also between girl and boy because they're age, they share a young age, king and queen because they're royal, and you can see that water is dissimilar from the rest because it's not a human. And more interestingly, that you can use some cool algebra with this and subtract and add representation to each other to make up a new representation for a new word. So, for example, here If you subtract man from king, you stay with royal embedding, maybe. And then if you add a woman, you maybe go to the queen embedding. And if you actually do that, and you compare between the embedding the model generates and the one that you calculate, you find that there is a lot of in common. Kind of it works. And therefore, you can make upwards from like quarter minus 3 plus, no, I don't know, like you can make things up and see that embedded and use that. So it's quite powerful. And remember, the model never been taught or trained to learn these relationships. Yeah? Just was learned to predict context word or a target word.
May I have a question?
Yeah.
Because it looks like we have feature selection, which you understand machine learning, so we like to condense many features to one more information. Yes. So the king minus man plus woman, we have a queen, yes? It's kind of density of features. So we reduce the number of features, so it's more like feature selection, and we like to have one. I know it's not fully.
Yeah, so
it's nice to have a solution. How do we decide? Is there any kind of methods to do this decision?
not really. So here, just for visualization purposes, the vector is small. But in reality, you use the big vector. So it's 300, you use the whole 300 values. So no feature selection. Okay? And to do this kind of relationships, it's arbitrary. Like think of any other relationship to generate instead of queen, I don't know, skating or skiing, and maybe add snow to roller skate, blades, and like you might get.
Our perception that we know what we choose probably as a humans, yes, but can computer learn which words to use to condense information and redact it?
So you mean this way?
Step, yes.
This step is human made. This is not machine made. The last step is machine made.
Okay.
So this is a human made, but out of the embeddings that's the machine generated. And the interesting thing is to look at these last 2 rows and compare, and just appreciate that the model was able to learn implicit relationships without us explicitly training it to learn them, right? Just to demonstrate how powerful this can be. But there's no feature selection So pretty much everything machine generated, just the step of subtraction and addition. Yeah. So far so good, I hope. But MLP is so this kind of where is it? Yeah, this kind of architecture is just like a feed-forward NLP kind of thing. Yeah, and there's nothing fancy, it's even fully connected. Yeah, and this is the most basic neural network, but it's basic neural network format. So we call it MLPs, multi-layer perceptron, and it's not the best in the world. It works, but there is multiple disadvantages when you use them. Because, for example, it always expects a fixed size input and generate a fixed size output. Okay, and also does not take sequential nature into account. So, for example, when you feed the context word, you don't tell the model which word comes first and which word comes second. You just say, these are the context words. They surround, in a way, our target word, but I'm not going to tell you the distance, the exact distance between these words and my target word. Yes, so kind of sequential nature is missing there. It is missing there. And then when you have a very long document, and you want to represent the entire document in one model, you can't do that because it will be too long for a model to take. And if you train your model maybe on 10,000 tokens, and you want 10,001, then you will have to break it in 2 parts just because you have 1 extra token and you want to represent that. So you even get rid of that extra tokens and don't model them at all. Or you just break or chunk your input into different sequences and feed them separately. But also the model will not know which comes first. So agree, it's valid. That's when recurrent neural networks appear. And recurrent neural networks are more sequential in nature, how it treats the data and processes the data. So just so to give you an example of how it works, I'll ask you to predict the missing character here. So it's A, B, C, D. Exactly. So easy, right? It's perfect. And Z, Y, X, W, V. She said you, but there's just like one or two voices in the room, right? But the E was much stronger, echoed from all the room, right? So what's the problem here? Our brains are trained sequentially. From a young age, ABCD, like the song, or like in any language, we will start from the first letter to the last letter in the alphabet. Our parents will never teach us to learn the reverse, although that would be super cool to show up in school. But parents have their limitations, and so we learn sequentially, and that's why it was very easy for all of you to figure out the missing character letter is E. But when we did it the reverse, you needed some thinking, like a pre-processing time. Yeah, I'm sure you'll all get it. You say it's you. Some will have like 10 seconds, some will have 1 second, but definitely E, predicting E was much easier, definitely. Right? And that's pretty much how RNNs work. So they do learn the sequential nature of the data. And they try to learn which comes first, which comes second, and so on. So the order is very important. So they are trained sequentially, one word at a time, and the same input can generate different outputs, depending on even the previous context. Yeah? They have a shared memory. Memory is important because that's what, as a human, that's also what we use our memory to remember the order of these alphabet characters, right? And same here. So we have a shared memory and we have a sequential mechanism of building the words. It's recurrent, so it feeds to itself, and the memory is represented by the shared weight. So before, each neuron had its own weights or unit, had its own weights forward or backward. That's the connections, right? Here, when you feed the first word to that recurrent unit, it will process it. Let's say you feed the second word, the same unit will process it, and the same weight will be updated. So the connections for all the words in a sequence the same. Okay, and that's the shared memory. You can see there's some weight. It's here, ST minus 1, ST, and ST plus 1 says over time, T reflect the time. Yeah, and pretty much this is you unfold it, but it's the same. We don't have 3. We have just 1. It's updated on multiple time steps. Yeah, and what you update your W matrix would be the weights between your hidden units or the specific neuron and between itself and itself because it's recurrent, and also the weights between the hidden units and the input, and also between the hidden units and the output, sometime when you decide to spit an output. So here, we're spitting outputs at every step. So maybe it's one-to-one relationship, and maybe it's like a summarization or translation, and I'm expecting you to spit text at every time step, right? Sometimes you don't have the output at every time step, you have it just at the end, and it could be classification, positive or negative. So, but the weight matrix would be hidden between itself and itself, hidden output and hidden input, okay? And that's shared with everything else. To look inside what exactly happens here, the basic version is also to use a tan function and non-linearity, normalize it between -1 and 1 values. And you can see the weight matrix here between the hidden and hidden X. X is your input, and then you calculate your new hidden state and you update the weights accordingly. Also, don't forget about your output when you want it. Then you just calculate you calculate it from the hidden state itself, but using the weight matrix between the hidden and the output. Yeah. So we also don't like this. Yes.
Are the weights always the same or different for this box?
So the weight matrix is shared with all the inputs, like it is the same, but the weights for the hidden output and hidden input are different. But over time they're the same, so they get updated over time. Yeah. So before we saw that, for example, x1 and x2, let's say these are two words in a sentence, they had their own different connections. Here, they have the same connections. They update those connections. Yeah. So we don't like RNN, we've been decided. Why? What's the problem with RNN? So when you feed language to RNN, and let's say you have a very long document, it will tend to forget what it saw at the very first of the document. So let's say you're training it with, the longest Harry Potter book, and some name appeared at the very beginning, and we did a question answering task and answered what's the name appeared in the first page. Most likely it will not be able to tell you. It will be able to give the answers maybe for the last page or so, but tend to forget what happened before. Yes, because it's adaptive, the weights, think about the weights are always getting biased toward what it sees at the end. Because what's updating the weights is what is the most recent stuff we're feeding it with. Right? Somehow, the weights that it's learned for the first words getting diminished in a way. So this is a problem, and something called long short-term memory cells address that. And they try to address that, so before we had the input, right? Nothing new about the input. We had the hidden state, also nothing new with the hidden state, right? This is our H. This is it, and also we have an output, okay? So we have the hidden state, and we have an output, but we have an input, but the only, or the most important addition to LSTM is the cell state. So your superhero is the cell state. And we expect the cell state to retain information from the past, but also from previous states itself, but also be able to decide or give it the functionality to decide what to remember and what to forget. Because you can't remember everything. So maybe something that became irrelevant to the current context, you can't forget. It is powered with multiple gates. So you have the forget gate, the input gate, the candidate gate in green, and in purple your output gate. I find it easy to remember which is which when you look at this diagram as the multiplication here with the forget gate. So I'm kind of telling you this is a forget gate because this is a sigmoid. Sigmoid spit out values between 0 and 1. So if you multiply by 1, you're keeping everything. If you multiply with a lesser value of 1, you're kind of forcing to forget. If you multiply by 0, you forget the entire thing. Right? That's the easiest way to remember. So the forget gate would reduce context or keep it as it is. They all use some sort of activation function. So input gate and candidate gates, they use sigmoids in tan, and the input gate, Y, you have the summation on top, and you sum information, you add information. You can decide not to add anything, or something from the new hidden. And then you have the output. And the output then with the output kit will calculate your output for you. Okay, that's somehow a hint on how to remember which is which. When you see this diagram again, because I know for my students, they like see the diagram without clues, and it's like, okay, where is the forget date? And they forget what it's called. So the easiest way, and this is really how it works. You see that all these now have their own weights. They're shared among, because it's also recursive, so they are shared, but they are separate. They're trainable. And you also have the weights for your hidden and units and your input and output as well. Okay? And you update the cell state and you pass it from one time step to another, so on in the future. Same for everything. Make sense? So that's kind of LSTM solved some level of the problem. I'm going to criticize it later on. So, but in many applications, especially when you have small data, it's great. It is very expensive though, because you're updating so many things. And it's sequential, therefore you can parallelize it. But there is another variation, is the bidirectional version of it. The bidirectional version is sounds a bit more complex, but actually it's identical to what you saw before. But instead we have two layers or like two models separate in a way. And one will see the text from first word to last word, and the second one will see the text in reverse. All right, so it will learn the reverse version of the text. The one extra thing that they do is they can concatenate the hidden states together from the forward version and the backward version. Okay, so exactly like before, but with an extra step, and that's a concatenation step with the hidden states of the forward class and the backward class. But these two are separate. To make things more exciting and give it extra capacity, you can make it stacked or deep. So before you saw maybe up until here, and we decided that maybe we include an output, maybe not, maybe not at every time step, maybe yes, depends on your application. But here we added like 2 extra layers, and maybe you can add 1,000 extra layers. That's up to your application and your preference. Does it add complexity? Computational complexity, yes, but for your model, you're just adding a layer. And remember we said we have hidden input and hidden output. Well, you have an extra weight matrix here for hidden between the layers. So hidden L to L minus 1 and L plus 1 possibly, yeah? And then you do the calculations depth-wise, and then you move in time. Yeah? And that gives you bigger capacity for the model to embed more information and relationships. So what's now? We learned about all this random stuff. What do we use them for? One of the very important applications for these models is the machine translation task. Yeah, and the translation task played a big part in NLP development generally. And specifically, you might all heard of transformers, and transformers was born from a translation task. Okay? So, we call it sequence-to-sequence model because you give it an input and you give it a textual input and you expect a textual output. Yeah? So, you feed it with a sequence and it should generate a sequence. It has an encoder and decoder. Encoder will try to embed all the information in your input text. The decoder will rely on this input representation and then try to produce the output sequence. Can you think of any other task, like sequence-to-sequence task, beside machine translation? Like maybe summarization. Summarization, you get the text, it output text, right? Anything, like you also,
Maybe speech to the text.
Sorry?
Speech to the text.
Speech to text, but speech isn't, but it should be text to text, though. The speech is an audio signal, so,
Grammarly?
Sorry?
This app, Grammarly?
Grammarly, yeah. So fixing grammar. Or giving suggestions to fix grammar. Yeah.
Or these softwares to write a review out of a bunch of paper.
Yeah. Write reviews, paper input, review as an output. Great, and pretty much that's what's happening on a much worse quality these days, but at least if we automate it, we can pick the good reviews and make sure the models train all good stuff.
Answering the questions, continues as well.
Yeah, dialogue like a chatbot kind of thing, an input and a response as an output and so on, exactly. So this is very useful, right? And even you can maybe think out of the box and say, can I use it for genes or can I use it for something that has nothing to do with words, but something to do with tokens. And you define what your token is. It can be anything. It doesn't necessarily textual token, okay? So in translation, usually we feed it the source sentence, and that's the language you're trying to translate from. And the output would be your target sentence, and that's in the target language you're trying to translate to. So, like, this is pretty much a simple version. Like here you have, like, visualize it in your head as an RNN or STM. That does not matter, right? And here again, LSTM or RNN, some sequential model on the right and sequential model on the left in the decoder and encoder. And then this first RNN processes the input text, the input sentence from the source language and try to predict the output or the target sentence in the target language. So try to spot disadvantages because, I like problems. But like the decoder, when it tries to do the task in hand, translation, it will rely on, for example, this step here, it will rely on the word before the decoder tried to predict, and also the context from before, and that's coming from the encoder, right? And to generate an output. So the decoder does not only rely on the source sentence, but also to keep the output in context. It also relies on the output it generated so far. Yeah. So at least the grammar stay correct.
How about the languages that have very different order words in the sentence, like German?
Yeah, so it doesn't have to be word-to-word like so. Remember here, it doesn't have to be word-to-word. Translation is a very interesting, tricky task because sometimes words don't have any translation. There's like a blank pause in one language, and the second language or the target language shouldn't output anything when it sees that specific word from the source language. Or maybe it should output 2 words or 3 words, and this is possible. So it sees the previous words, So this one is seeing the previous force that it's generated itself, right, which is fine, but it sees all the entire context from the source. So this could be a relationship between like 4 to 10 or 10 to 4, right? It's not 1 to 1, because it looks all the context every time step. The decoder looks at all the context on the encoder at every time step, and also the context it generated so far. It's conditional because it's conditioned on the source sentence, right? It has to be a translation. The decoder can just start hallucinating and generating random text, although it might make sense grammatically and stuff, but it should always be a translation to the source, so that's why it's conditional. And it is a language model because it can generate text. Right? So the decoder by itself is a language model because it's generating text conditioned on the encoder. So here, the decoder, where is the problem? What do you think? Where is the problem? Where is the problem? Like, it does work. This by the way, do you remember if you're in the NLP news a couple of years back, before BERT and GPT and so on, we saw the big stars in language models. Before that, there was something called ELMO. Have you heard of ELMO? And ELMO is like bidirectional model like that, sequential using RNN versions or the like. Yeah, just to give you a hint that this is what used to be a breakthrough in science for a few months before Google starts training their but yes, where is the problem?
Maybe the inputs will be forgotten quite quickly. So, like, there is only one input from the encoder, and the gradient will vanish until it goes to the.
So you're saying the input. What's the problem with the input in the encoder?
That it's only like the decoder only once there is input from the encoder.
Yeah. So
it can like forget very quickly what was the encoder.
yeah. So you think the decoder can start forgetting, right? Yeah.
Maybe the problem is in that. Maybe the problem is in article there. Maybe just like the article there is associated with such many words.
Yeah.
Maybe, it's just my guess. When you start giving the word exact as input,
Yeah.
you can get literally anything.
Yeah. Yeah. It's like a start as a start token, right? Yeah. So this is a problem, but this is solved by telling the model when it starts outputting. Maybe I forget to talk about the start token here in the decoder, and it's a signal that you can go on and start generating. And also the decoder will generate the token end, and that's an indication as stop. That's it, the task is finished, and we generated the output. But what you said, what's your name?
I don't know.
Very embarrassing myself. Alona. So Alona is very, very close to the right answer. But yes, like the decoder will have to go and rely on this context box. This context box is the last hidden layer in an RNN, for example. So it's literally relying on the last hidden state in an encoder. And this is pretty much influenced by the last word the encoder was fed with, right? It's using this to generate a very long sentences, maybe, as the decoder might decide to generate a longer sentence than and maybe we're translating paragraphs, not sentences, right? So an entire paragraph meaning is squashed in the last hidden state of an RNN, And somehow, magically, we're expecting the decoder to go and just look at this very last hidden state and translate the entire paragraph. Right? It's a problem. Problem because the longer the context is, and the longer the input is, the more the encoder will struggle to produce a good representation for the decoder. And the decoder will start underperforming. Yeah. So we call this problem. We call this problem a bottleneck problem. The bottleneck because again the decoder is relying on this bottleneck, and this bottleneck is filtering the meaning from the rest of these hidden states of the previous words. So what's the solution? You've heard of attention? So attention was born in 2017, and the paper was called "Attention is All You Need," after the Beatles song. But then another paper here said attention is not all you need, and so on. But attention was a very big, important step in the NLP development. And it's very simple, and it added interpretability for the model, so you can see what's going on somehow, far away from explainability though. So what does the attention do? It first calculates some attention scores. I'm going to speak about this in details later on, so don't worry. And then attention distribution, later on attention output. So we have attention score, distribution, and output. 3 simple steps for the attention to be calculated. The idea is, remember this, or I have this thing here. No. So, you see. So you remember this thing here, right? The encoder units. We had a bottleneck here. This was our bottleneck, right? And then it went to the decoder. So this is all here, old stuff. So this first layer, like just old stuff. You know that. The thing was that every unit in the decoder used to look at the previous one as from the decoder itself, and also look at the context box, right, or the bottleneck box, and that's it. Here, the idea was, well, why not allow it to look at all of them, all the hidden states, all of them. Yeah? So instead of just using a bottleneck somehow to generate a big target sentence, you'll allow it to look at all of them all the time. So the first word the decoder will generate or predict will rely on all of these hidden states in the encoder, not just the last one. But then it's like the concept becomes a bit like more complex, because you will say, but maybe it's looking at useless words, right? So that's where the attention comes to calculate the importance of a specific word to generate a specific output word. So here, you start with the attention score, and the attention score is just a dot product by the current hidden state in the decoder you're at. So it could be any one of those. Let's say it is the last one, and it's a dot product with every hidden state in the encoders. Yeah, and then you will have some values. These values then they're called scores, and then they will be passed to softmax. The softmax will normalize things between 0 and 1, and that's very useful because it gives you this very nice interpretable output to tell you when it relies on the last word the most. But that's not enough, because we want an attention output to go on and work with later on to replace our context box or the bottleneck box before. Yeah? And this is generated by just multiplying the attention distribution output of the softmax with the actual input again. Right? So when you multiply them together, the first 3 units will kind of be ignored because they have pretty much low softmax values. And then the last one will be highlighted more in that's reduced embedding, as the attention output, because it has a high value. Yeah? There's a lot of, you'll see a lot of applications generating or using this attention to highlight words in like color heat maps, maybe green and red. Green in the word is not important, or like the levels, and red is it's important to make a decision or to generate text. Yeah, and that's somehow that gives the entire thing more reliability. Maybe it's fake reliability, no, but it gives some reliability, especially when a human is using it and does not understand the technology behind it. Like you see, like, it does make sense because it's relying on the correct words. But that's very important. That's very important functionality being added to the sequence-to-sequence model, right? So this thing, including the bidirectional technique that you saw before, generated Elmo model, which is one of the most successful language models before 2017. But again, we don't like this. Why don't we like this? What do you think? So the main problem, like we remember we started from MLPs are rubbish. They're not using context because they just see the word as independent words. And then we moved to OR, and they're great because they're sequential. And now here, we're going to argue against RNN and favor MLPs again. Because we're going to say, well, they are sequential. It's so expensive. So if you have very big input, like millions of documents, when you have to train sequentially, that takes forever, right? So it will always limit you with how much you can train the model, because you can't parallelize it with GPUs. That was a big issue here. And also, even if you use attention and so on, still the model can forget things that's so before, like far away from your current input. So there is still these 2 issues, but the biggest motivation to move away from RNN again was the curse of sequential nature. Yeah. So literally computation. And then who do you expect to solve this problem? Well, the people with a lot of money and a lot of computing power, therefore the industry. And then something new was born. But technology-wise, it used similar things as you saw before. Right? Like similar technologies and similar functionalities. And some extra things, but nothing very, like, technically very surprising. But the main thing was let's ditch the RNNs kind of models, LSTMs and all of these, sequential model, and move back to MLPs, because MLPs and feed-forward networks are easy to train. And we can parallelize them. Yeah? But the main thing, they used a lot of attention. So they borrowed the concept that was proposed in Elmo paper, dropped the RNN, and trained on a big scale. So they really make a massive difference, yes. So see this example? This is my favorite example in the Google blog they've written about the paper. And you can see their output. This is a Google search, right? So before and after birth. And before you can see they're Googling parking on a hill with no curb, right? So no curb. And before, it used to give results. The first results would be parking on a hill, uphill, And when headed uphill, add a curve. So you already lost interest, right? Because you're searching for parking with no curve. The second one, after using BERT and transformers, and the output is much more accurate for either uphill or downhill parking if there is no curve and it continues. Right? So it's probably we would get used to get this kind of results and scroll down a little bit and find the answer. But here, it's generating the first answer with exactly what you searched for. So pretty much more accurate and very impressive. Just that changing the model, you were able to improve the technology significantly like this. So maybe some of you saw this diagram. This is like a super famous diagram in the paper. And it's, you have an input embedding, positional encoding. I'm gonna discuss it with you a little bit later on. You have multi-head attention. Remember, pay a lot of attention. So you've heard of attention, use multi-head. You just saw you do it X number of times. Add and normalize, just matter of addition and normalization. You have skip connections here, for example, and then feed forward. And these are the ones that replace the RLNs, processing units, with feed forward. And then again, add and normalize. This is the skip connection with normalization. You see, yeah. And again, here is the decoder, and the decoder again has masked multi-head attention, so it's very similar to the encoder, but it's masked. I'm going to talk about why later on. Skip connection here with normalization. Remember with translation, like the one we saw before, we apply attention between encoder and decoder. That's a cross attention between the encoder and decoder. Here it also does the same. In this step where it looks at the encoder and it applies attention between the encoder and decoder, add and normalize again, feed forward, that's the processing units there, and then linear layer and softmax to do whatever task you want to do, like translation, for example. Yeah. So the problem we talked about it is before, like the sequential nature and so on. But here, what they invented, kind of, but pretty much based on the attention you saw before, and started calling it cross-attention to distinguish it from self-attention. They propose to use self-attention. Self-attention is in between two target and source components. It's between the same source itself, with itself, and same as target with itself. I'll show you later on, like in the next slide, the values and query. Before, we had the encoder bottleneck or the encoder hidden unit and the decoder specific hidden unit, and it was looking at all the encoder hidden units, right? And we decided here it makes things a bit simpler because we are going to use the source and itself, no more encoder decoder, so terminology will get messed up a little bit. Decided to call the decoder hidden unit query, and then the encoder hidden units keys. And you remember when we calculate distribution attention after softmax and we multiply it back with the encoder hidden units? So when you use the hidden units of the encoder opinion, we will call them values. So keys and values for the encoder, query for the decoder, okay? Let's look at it here. So we call this. And every time step you're going to use only one, right? But then multiply it with all of them. So this is a query, and these are your keys. But then again, remember the attention distribution. To calculate your attention output, you multiply attention distribution with your encoder hidden units. We're gonna, when you use them again like this, we're gonna call them values. So just literally the same thing you saw before, just gonna add some extra terminology. Why? Because when you apply self-attention, you don't have a decoder. So you can't say the hidden unit of the decoder because that does not exist. You will say, I multiply the hidden unit of the encoder with itself again, after you calculate the distribution. To make it simple, add the terminology. I justify that terminology. So, self-attention, you have the same input, right? You have the same input, it's self-attention. You have the same input. You have different weight matrices, like why don't you use the inputs 3 times, identical inputs 3 times? Because they argued it's a bad idea if you have a single representation for the input and overusing it. And would it be a better idea to learn different representations for different steps? So you're learning more about your input practically, and then use it in these 3 different steps. So that's what happened. You have 3 different weight matrices, and these trainable, so they will be updated during training phase, to generate your keys, values, and queries. Okay? So you have your input, you introduce extra weight matrices to train, and this will produce your new representation of the input. But keys, values, and query, they all represent X. To the X. Similar to attention as before, remember we calculated the dot product first between query, which is the decoder hidden unit, and the key, which is the encoder hidden unit. So between decoder and encoder in the old layers, like previous slides ago, but here between the input and itself, because they both come from X. And this is your attention score. With a softmax, you get the distribution, the attention distribution, and when you multiply it back with a hidden unit, and but here with your values, the third representation of your input, you get the attention output. Yeah, and it's self-attention because query, values, and keys, they all come from X. You scale it because usually it's better to keep the values in line, and you scale it by the size of your vector between keys or query. Value can be of different size because now you're scaling, like you are learning different representation, and it's up to you to learn a lower dimensionality representation or a higher dimensionality. Usually you would learn lower dimensionality representation. Yeah? But because of that, here you can actually learn a different dimensionality for V or values than the ones for key and query. Okay? Just mentioning this because if you go on and read about this and find out that values have different dimensionality, you get confused. But you're allowed to have it because it's just given to a multiplication with a softmax output, like a probability distribution. Okay? So let's look at how it gets calculated. Look at the second input here. You have your second input. You generate 3 variations, right? You generate the query here in purple, keys in orange, and values in blue. Okay, and these are 3 different representations for your same input. What do? Remember, you have query and values should generate your attention score. Softmax, you get the distribution. But first, attention score, right? For all of them, because it will look at all the inputs around it, because the decoder, remember, looked at all the hidden units in the encoder. Okay? Is it clear, or am I losing you? Losing you? Did I already lose you? Too late. No, seriously, like, are you still on track? Yeah? Yeah? Too long, it's fine. I'm gonna just keep looking at you. So yeah, like no, that, like okay, I'm afraid I'm repeating too much, but if you feel that I'm becoming boring, so I can continue. Okay, I'm not becoming too boring. So remember again, last time. Sorry for boring you, but in translation it was easy because we had decoder, you had encoder, you had decoder hidden unit, right? That's relying on all the encoder hidden units to make a decision and spit out the translation word, right? So it was easy, like the attention looked at all the hidden units in the encoder, did some calculation, dot product, softmax, and so on, yeah? And the hidden units in the encoder were used twice. One, dot product with the decoder hidden state we're at, right? And then again, when we calculated the output, when we multiplied it with the softmax result, right? So hidden units were in the encoder were used twice, and the decoder once. Yeah, through the attention calculation before. Self-attention, identical, but you're going to look at the same input. So decoder and encoder are the same. So you're looking at the same sentence in the encoder and decoder. So you don't have a decoder anymore, kind of. Yeah? Because you don't then you have an input sentence in the encoder, kind of, and also the same input sentence in the decoder. Because you're trying maybe to predict next word or a missing word or anything. Yeah? But you are caring for a specific sentence only, and you don't care about the translation right now in self-attention. Okay? So you have your input, and you have two inputs, but it's the same, so it's kind of three. And I'm going to keep my hands like this. Okay? Before, there are three, the same input, okay? But we don't want to use them 3 times. We don't want to use exactly the same vectors 3 times. So we decided to transform them into a different space, maybe lower dimensionality, higher dimensionality space, up to you, yeah, to decide. Usually lower, but let's forget about this now. We transform them to 3 different representations, but they all originated from the X, our source sentence, yeah? And then, because before, like the decoder, we had it here, and then we used the encoder in the state twice, now 3 times, but again, they're all the same, but anyway. To differentiate, we'll call this one, we're going to use it as the current word in the prediction. We're going to call that representation query. And then we're going to call the 2 other ones keys and values. Keys will be directly interacting with query, right? And that's encoder decoder all the days. And the values, remember when we have the softmax output and multiplied it with the encoder hidden units again, that's our values. So the values will be multiplied. Yeah? Okay? Yeah? Something what they do. We have to feel it enough.
I have a stupid question. What query here is actually is. So what actually query is doing here?
So the query is taking the place of the decoder hidden state before. And it is the same, it is a projection of the input, just like keys and values. So if you have them of the same dimensionality, keys and values and query, at the very beginning, you can choose arbitrary. I want this representation, and I call it query from now on during the entire training phase. This is the values and this is the keys. You can swap them around at the beginning. So once you start training, because they have separate weight matrices and they get used in different steps, you can't mix them again. But at the beginning, they're all originate from X. So you call them whatever you want, like. But query, because that's your word you are trying to predict, and you're trying to say, I am at, so here I'm at the second word, input 2, and that's my second word. So to predict the second word from the context of this sentence, right, I'm gonna call that query because that is the word I'm trying to generate representation for, or predict, or see how much it relies on the context around it to make that prediction. Okay, so So every input token will generate 3 representations. Query, here, keys and values. Okay? Keys and values will be generated for every input. Remember the decoder hidden states, they are representing different words, right, in the same sentence. So keys and values for every input token. Yeah? But the query only for the word we're at, trying to predict, like a decoder concept, kind of.
Can you please give us an example, like take a sentence or just a phrase, and like what it's our input, and we want to translate it, and then like what is a keyword there, what is a value, what is key?
Yeah, I can. Give me a sentence. Very bad.
I love NGSchool. I love NGSchool.
Yeah. Slightly more context, because when you say I love, it could be anything. Maybe something more like contextual. So it actually relies, like, because predicting the school will be different. You can, I love my laptop, I love my child, I love my dog, and then I love the school. No precise context.
I buy bread at the bakery.
I buy bread from the bakery. So let me try. So I buy bread from the bakery, right? So bread, let's say our input, we're currently starting at bread, right? So bread is our query because we want to kind of try to generate bread from the context around it. So we want to pay attention on all the words in the sentence to generate the word bread. Yeah? So every word, so I buy bread from the bakery, every word will have values and keys. Okay? Values and keys. Let's say keys now. They will have keys. So some numeric representation. Okay? That's learned through training. So they have these vectors. And then bread will have the representation in query, we call it, and another representation as keys. Okay? So this is currently our bread word. Yeah? It has its query, and then I buy, maybe buy bread bakery. Yeah? And maybe here, buy, and here, bakery. And bread and bakery have keys and values. Okay? And let's just focus on keys at the first step. Okay? But the only word that has query is the one we are at, and we're trying to present it like predicted, let's say. Okay? Yeah? So we have the query, because that's what the word we care about, the bread, and we're going to do a dot product or multiplication between the query of bread and then the keys of y and itself, bread, and bakery as a third input. Okay? You multiply them together, and then you calculate softmax, and you have some distribution, attention distribution. And then maybe attention distribution will tell you, will be very high for bakery, because you get bread from bakery, but you can buy anything. You don't have to buy bread, you can buy water, right? So maybe the highest attention would go to bakery in the softmax result, right? But then you also, to calculate the attention output, you multiply your softmax with your x, but which representation? The values representation of your x. Yeah? So you multiply it again with values, the blue box here. Yeah? And you sum them over, and you get your attention output. Makes sense? Now? So you are in the same sentence, and this wording question will move. So here you will have bakery as your word in question. Bakery will generate a query now. So you only have one query at every time step. And this query only belongs to the word you're at this time step. Okay, so here bakery, it has query, it has keys and values, but all the rest of the words have encoded within units, so they also have keys and values. Okay. Now to calculate the attention score, you are going to multiply your keys with your query, right? All the keys with a query, and then you do softmax, you get the score, and then you again to calculate the attention output, you will multiply it with your values. Yeah, and maybe here by bread bakery, maybe bakery as well will highlight bread. Now this softmax results don't make any sense because this is not designed for by bread from bakery. Yeah, but like if it is the case, then when you're at the time step of bakery, at the word bakery, probably bread will have a high softmax value. Yeah, and then these scores will be multiplied by the value representation vector of your all the words and give you some attention output. You sum them over and you get this. And then you work with that. Makes sense? We have more moving heads. You want me to repeat? No, seriously. Is it clear?
Does this happening sequentially word after word?
It doesn't have to happen sequentially, right? Because you can parallelize these.
The point that they're all kept.
Yeah, but you do this like it's, like with transformers, you do this so many times. All inputs in so many times. So when you parallelize, you gain a lot of time, computing time. Yeah, because these can be done separately. The calculation.
The number of the words that are looked at the same time, so in this case 3, it's a matter of choice.
Yeah, matter of choice. Yeah, so maybe it could be 100.
But is it representation of the words we get from the word connect, from the previous slides, or what's the representation of words?
So this would be different in nature, right? Just because word2vec stuff, the representation of the word, because you train and you freeze the model, the representation will, and there is no context, the representation will be fixed for the word regardless of its context. So, for example, buy will have the same representation vector, whether it's in a sentence like buying a dog or buying drugs. But, yeah? With such model, with such attention model, you will have different representation. Because it takes, when it does the calculation, it takes into account the words surrounding that to calculate the attention output. So if the context was around drugs, you will have buy in slightly different representation vector than when it's about dog or bread. Yeah, things like that. And the very common word is bank, like the bank to withdraw money or the bank of the river. And word2vec, they both have exactly the same representation vector, exactly. And something like this model, you will have different representation for the same word. But because something is like contextually and semantically, they have totally different meanings. Yeah, so you did gain more knowledge about the words and the context in from your input or from training data. Yes, so you will see today Sean will show you how to use BERT, and it does a transformer model, and you probably can demonstrate that when two words, bank of the river, and I'm putting pressure on your shoulders, sorry Sean.
So how do you choose the transformation matrices for value?
So you have like weight matrix, and you probably start just from random weights, and this is trainable.
It's just like additional trainings.
Yeah. Yeah, and the model will have to find the right representations to increase performance. So this is all trainable. You don't set the values of these values or anything. Yeah. Happy to move? Yeah? Good stuff. I'm over time. Yeah, well, I'll try to hurry. Yeah. So we like you saw, we do attention. It looks at the context, and yeah, well, we do parallelization. How much we gain? The thing is, we gain a lot because this attention does not just happen once in a transformer. It happens 100,000, tens of thousands of times. Depends on the size of your model you decide on. So generally, we would have a multi-head attention. A multi-head attention is just the same attention done X amount of times. This is usually 8 in the original paper, but then that's exceeding that significantly now. The more you use, the better performance you have. And this step, the self-attention in the encoder and decoder technically is the same, but the sentence is different. Yeah? But in the decoder, because you're decoding or you're predicting words in your target sentence translating, you're only going to see until the word you are currently predicting. Otherwise, you'll be cheating because you're looking ahead of time. And in reality, in inference time, you don't know that values. Okay, so that's the only difference. And we call it here masked attention because you are trying to predict the word. In real life, you don't know this word, so it can't really pay attention to itself because it does not exist yet. It's yet to be generated. Encoder does not matter because source sentence is given. Okay? And technically, is very basic. You do the attention multiple times, and then you calculate the results. Residual connections. Maybe you heard about it before. It's heavily used in deep learning generally and in computer vision as well. And skip connection is to kind of remind the model of the original input. So after a lot of processing here and there, it might maybe generate something far off, and maybe by this is going to be very deep model usually, and it's the original good representation that we're working on get diluted, and so the residual connections will just literally add the previous input from the step before to the output. And that's element-wise addition, and then you normalize. Yeah? And again here, it happens the same. I'm saying element-wise because in these models, they make sure that the dimensionality stays the same throughout to make computation easy. Yeah? Linear layer, you've probably been linear models. The linear layer is pretty much a similar job. And this is just a fully connected layer with your current output, because your current output will have a dimensionality, maybe does not match the vocabulary. And you are predicting words from your vocabulary. So you want to move from that arbitrary dimensionality your model is producing to your vocabulary size dimensionality. Yeah? And that's what you use the linear layer for, to just move in dimensionality to what you need. And later on, you use softmax to calculate probabilities of the most probable words to be outputted at this time step. Okay? So we said multi-head attention, and they happen so many times, like 8 heads originally, but now 10s. Also, the encoder isn't just a single encoder, or in the original paper, they proposed 12 encoders and 12 decoders. Now, this number was exceeded and multiplied. So you just, the model itself isn't very complicated, but it becomes complicated when you add so many encoders, decoders, layers, and attention heads. And people might ask, well, what can attention head, when multiple attention heads do better than a single attention head? Empirically, it appears that in training, the model is much better performing. So multi-head attention is important during training, but in inference, you actually can get rid of most of the heads and just use one or two because they replicate each other's jobs. Yeah? Remember, every attention head has different representation of the input. So you have query 1, query 2, query 3, so on for every. So very likely you will end up with a representation look like each other. Yeah, but it's important for training, not much for inference time. Decoder is also the same. It happens anytime, maybe 12 or more. The main differences here, you have the masked head attention when you mask the word URI, and also you don't allow it to look ahead. One interesting thing to mention is that the decoder is trained in an autoregressive way, meaning that in training you allow the decoder to look at the ground truth of the predicted words, the actual words, not the predicted ones. So it makes a better job, but of course in inference you don't do that because arguably you don't have the ground truth. Yeah, so that's the autoregressive we call it. You allow it to look at the ground truth during training, but you do it properly with end-level data during inference. Yeah, and it works better this way. So, BERT. BERT is one of the, sorry, did I over time?
That's fine.
Should I just get, no. Is it okay?
No, it's okay. Like you chart, you can.
I'll be very fast. I'm very sorry. Didn't expect so much. So BERT is a transformer, but you get rid of the decoder part. Okay, you just throw away the decoder part, and you end up with an encoder, and it will generate words. But you know the encoder part learns from the entire sentence. So the trick part is to mask the word you are at and just predict that word in the output. Okay, but just use the encoding part. There's two tasks there. One is to predict the masked word, and that gives us the ability to generate feature representation or word representation for that missing word, and also next sentence prediction because it introduces the token for classification in the output, and it allows it to do classification tasks as well, not just word representation. GPT, you might have heard of it, also is heavily based on transformers, but you get rid of the encoder, you rely only on the decoder, and you might know that GPT generate text. It's not, they don't generate a missing word, they generate the next word or word, right? So it's a text generation model, and that's why you use the decoder here. And you leave it as it is, exactly same concept. No new training tasks, but you just remove all the encoder with also the cross attention here. Yeah? I have shown this video. Yeah, kill me. Sorry.
Very good book. You just say silent version.
Yeah, like here you use GPT. That's the older days, like GPT-1, I think. This is like pretty much an old GPT, and you use it to generate web pages from free text, so zero coding, okay? And you say like a header that says mood tracker, press buttons, and it has to output the mood in text. Remember, you haven't put any code there about buttons or so. Indeed, you click and you get that, and it does generate the text for you. You make it even more interesting, and you say output emoji, not just the word, because you might say, well, I'm giving it the word anyway in the text, maybe just for me to output that word. And emojis never seen emoji in your data, but probably in the previous training, and it does work. And it generates code for you. So if you have a homework to do a web page, you just use this kind of stuff. Language models are problematic, so and now Google fixed it, but they fixed it superficially. Language models they use still success. And here you see like an anti-stereotypical statement. She invests, he washes laundry, she plays sports, he takes care of the children, she works, she dances, she drives a car. Anti-stereotypical statement, yeah? So this gets translated to Finnish, and Finnish is genderless language, so everything turns into them. Like, and then back to English. And when it's back to English, stereotypes. He invests, she does the laundry and kids and stuff, and he's successful in doing work. Yeah. So, but that's because pretty much the web data is rubbish, and people say things on the web they're not supposed to say. They wouldn't say in real life. Also, how about misinformation? You'd think language model, well, you might be more impressed of vision models more than language, but, and you probably also heard of deepfake and get very impressed by it, but deep text or generating misinformation using language models is even trickier for human beings to detect than deepfake itself. So if you're impressed with deepfake, be afraid of language models. This is also a big problem with political campaigns and so on, anti-vax and all this stuff. And these were tried to be used in a medical application. So you see here someone's trying to book an appointment. That's an OpenAI work, and pretty good. You get a conversation, you book an appointment, and it's very like a human-like conversation. So pretty successful. They tried to use it in a mental health application, and yeah, like an advice to a depressed person to go and kill themselves. Yeah, it's not very funny, but it's not funny. But it just shows you how toxic and dangerous these models are when they put in the wrong hands. I love this slide, I have to go to it. Reveal bias using adversarial exam. So when you build a model, maybe a lot of you heard of toxic detection, toxic language selection, toxicity score estimation with language models. And usually it's really good because it looks for the offensive words and give a high score. So usually they perform really well in these models, the toxic language models. But if you if you input some statements and then look at the output, it's interesting to do some comparison. So bias toward identity, you see statements like the Gay and Lesbian Film Festival starts today. There's nothing wrong with these statements, like being transgender is independent of sexual orientation and so on. Muslim is someone who follows and practices Islam. Like this is factual statements, and you find a pretty high toxic score there just because there's certain keywords. So you feel like even in the Muslim stuff here, it's 0.46. You say, it's less than 5, but it should be 0 because it's not toxic at all, right? Bias towards entities. This is interesting. I hate, both of them I hate, right? So it's hate, so it will be toxic. But if you hate a woman, it's less problematic than hating a man. If you hate a man, you're very trouble, you're very toxic, 90. But if you hate a woman, 69. Interesting stuff. I'm a person not toxic at all. I'm a tall person. This model loves tall people. I see 03. I'm a blind person, it goes up, doesn't like people with disabilities. Deaf is even worse than being blind, but why? No one knows. I'm a person with mental illness and it goes to high top sex score. So you feel even if it was biased against mental illness, you see there's also a distinction between them and has its own biases depending on what disability you have, which is shocking. And the problem is you might say data is biased, therefore it's biased, it's nothing wrong, like we are crazy people and we generate crazy content on the web. It's our mirror and all this stuff. But the problem is that it amplifies bias. So in this study, they use 67% cooking images have women, right? So 67, so it's biased towards women. And the model predicts 84 women cooking in the test set. So even if the test set has the same distribution as the training set, it should predict 67, but it amplifies bias. They apply their debiasing techniques to reduce bias, and even though they do unbalancing data and so on, with all this, they drop it from 84 to 80. So it doesn't only learn bias, it amplifies bias, which makes it what to do. Always ask yourself, is it a good thing to predict? Will it help humanity? Who are the people it will bias against? Will it identify your vulnerable groups? Always identify your vulnerable groups. You work with genes, you always identify your vulnerable groups, your minorities and so on. You have enough data for those. And maybe you have even equal amount of data for two subgroups, but maybe one group's data is more difficult to learn than the other. Right? So bias isn't just about quantity of like 50-50 split of the data. The most important advice is work with other people from different domains and different cultures and different ethnicity background, and so gender and so on. The more diverse your group is, the more questions you will have about what about me? Like if you never include women in a study, it will only design a solution that works best for man. Even if that man is a feminist, it will still work best for man. Right? So always include everybody from all speciality, career-wise, and also from all culture and background and so on. No questions, because I'm You can